Every time you cry while chopping an onion, it is actually not the onion's fault.
No, it's definitely your knife technique.
Right. It is entirely your technique. Today, we are completely bypassing the basic recipe talk for this deep dive. I mean, you already know your way around a kitchen, but we are looking at the actual physics, the food science, and the biomechanics of professional knife work.
Because, the moment you understand the mechanics of the blade, everything changes. You stop fighting your tools and you start cooking with, serious intent.
Yeah, if you want to refine your skills, we really have to strip away the bad habits that, well, that even experienced cooks unconsciously develop over years of just, making dinner.
Absolutely. We have
You
to
know.
replace those habits with a rock-solid chronological foundation.
So we are diving deep into the architecture of prep work today. And it all begins before the knife even leaves the magnetic strip.
It's setup.
Exactly. You've probably heard the classic trick about stabilizing your cutting board by putting a damp towel underneath
Oh,
it.
yeah, the restaurant standard.
Right, but let's look at the physics of why that actually matters. When you are applying, say, 15 to 20 pounds of downward and forward force through a steel blade, a dry board on a slick granite counter creates this perfect storm for dynamic friction failure.
It's all about shear force.
Yeah.
I mean, a sliding board introduces absolute unpredictability into your workspace.
It's chaos.
It really is.
Yeah.
That damp towel acts as a physical anchor. It creates suction and friction, locking the board to the counter. Because if your cutting surface shifts even a fraction of an inch while you're, bearing down on a dense root vegetable.
That is exactly when a sharp blade deflects sideways.
Yes, and that brings us straight to the tool itself. We're focusing entirely on the workhorse here, the French knife.
Typically known as the chef's knife, right?
Right. Most people just look at it as a handle and a sharp edge. But there's an entire engineering logic behind the shape.
I was actually reading a study recently from an ER doctor who specializes in hand injuries. They were noting that a massive percentage of severe kitchen lacerations happen when people try to use the tip of the knife for heavy, dense tasks.
Oh, instead of the heel.
Exactly.
Well, that makes perfect sense from a biomechanical standpoint. The edge is really just the final point of contact, but different parts of the blade are engineered to absorb entirely different types of force.
So walk us through that. Why do we need to know where the heel or the spine is? Isn't the sharp edge the only part that really matters?
I mean, you'd think so, but no. The heel, that heavy, thick back part of the blade right near your hand, is your power center.
Okay.
That is where your leverage is maximized because it's closest to the fulcrum of your wrist. You deploy the heel for, splitting a tough winter squash or driving through the dense core of a cabbage.
Right, because trying to use the delicate tip for a squash means you're creating this massive torque on the blade. It twists, and suddenly, you are on your way to getting stitches.
Exactly. The tip is engineered for precision, scoring skin, or finely mincing a tiny shallot.
What about the top of the knife?
You mean the flat of the spine. That allows you to safely apply structural pressure with your guiding hand when you need extra weight.
So knowing the anatomy means understanding which specific zone of the tool to deploy for a specific physical task.
Precisely. And the absolute golden rule governing all of this geometry is sharpness. It's the great paradox of the kitchen.
The sharper the knife, the safer the cook.
Yes. People are instinctively intimidated by a freshly whet-stoned blade, but dull knives are the real menace.
Oh, totally. Think of a dull knife like driving a heavy car on completely bald tires.
That's a great analogy.
You have no natural traction, and because you have no traction, you have to overcompensate by forcing the tool.
Right, you muzzle it.
Yeah, you bear down hard to break through the slick skin of a tomato, the bald edge slips laterally, and it just hydroplanes right off the food and straight into your finger.
Ouch. Yeah, a truly sharp blade bites instantly. It requires almost zero downward force from your shoulder. The weight of the steel just does the work for you.
And when that surgically sharp knife isn't actively moving, the protocols are really rigid.
Extremely rigid. You never hide it.
Uh-huh.
You place it flat, well away from the edge of your station, with the blade facing away from you.
Never drape a kitchen towel over it.
Never. And you never leave it buried under a pile of carrot peels either.
Because reaching blindly into a cluttered prep station is just asking for disaster. And I think it's worth stating the absolute most crucial rule of gravity in the kitchen here.
The falling knife.
Yes. If you bump the handle and that knife gets knocked off the counter, Let it fall.
Immediately step back.
Do not activate your reflex to catch it. I mean it. A falling knife has no handle.
You can replace a chipped French knife. You cannot replace severed flexor tendons. Let the floor take the hit. Always. And, if you are navigating a busy kitchen space, the knife stays pinned flat against your thigh, point directed straight at the floor.
So our environment is stabilized, our tool is sharp, and our safety protocols are locked. The next progression is the physical connection between the cook and the steel.
The grip.
Right. A knife shouldn't just be held. It really has to become a fused extension of your arm. Let's look at the dominant hand.
If you are grabbing the handle with your whole fist, like wrapping all your fingers around it like you're holding a baseball bat.
Or swinging a hammer.
Yeah, exactly. If you do that, you are severely compromising your control. That standard fist grip is exactly what causes wrist fatigue and wobbly slices.
Because you are essentially fighting the weight of the metal.
Right. What we need to employ instead is the pinch grip.
For anyone who hasn't used it, the pinch grip means you still hold the handle with your bottom 3 fingers, but you slide your hand forward.
Right up to the blade.
Yeah, so your thumb and your index finger move past the handle and pinch directly onto the flat sides of the metal blade itself.
Now, I know if you are hesitating to put your bare fingers right onto the actual steel blade. I completely get it.
Wait, yeah, putting my fingers on the actual blade sounds like exactly what you shouldn't do. It feels so counterintuitive.
It does feel strange at first. But let's look at the physics of center of mass here. By choking up on the blade, you are shifting the center of gravity directly into the palm of your hand.
Oh, I see.
You are mechanically fusing the blade to your wrist. Think about holding a pencil.
Okay.
If you hold a pencil way at the back by the eraser, your handwriting is going to be incredibly messy.
Oh, yeah, and you have to use tremendous forearm effort to control the tip. You choke up right next to the lead for control.
Exactly. When you pinch the metal blade, you gain absolute lateral support. If you only hold the handle, the heavy steel blade acts like a pendulum.
Constantly trying to wobble side to side.
Right, and you're relying entirely on wrist strength to fight that wobble. The pinch grip dictates the movement through skeletal alignment rather than muscular strain.
That makes so much sense.
Plus, you gain proprioception, that sensory feedback of exactly where the blade is in space just because your fingers are in direct contact with the steel.
It is total directional control. So our dominant hand is completely locked in. But, the dominant hand is actually doing the easy part.
Oh, definitely.
The non-dominant hand, the guiding hand holding the food, is the one in the danger zone. How do we build a physical barrier to keep those fingers attached?
We rely on the architecture of the claw hand. I mean, this is arguably the most vital biomechanical technique in cooking.
Walk us through it.
You place your fingertips on the item you are about to cut, and then you physically curl your fingers backward.
Tucking them away.
Yes, tucking your fingertips behind your knuckles. Your hand basically mimics a bear claw. Your knuckles become the furthest point extending forward.
So it creates a literal physical shield, like a sheer wall of bone.
That's the perfect way to describe it, because the flat side of your knife blade is going to rest gently against those forward-facing knuckles.
So the blade actually touches your knuckles.
Yes, your knuckles are a guide rail. As you slice, your knuckles guide the lateral movement of the blade, while your tucked-away fingertips slowly inch backward, feeding the food into the path of the knife.
Wow.
So your vulnerable fingertips are entirely shielded from the cutting edge by the flat of the blade resting on your knuckles.
I will say it takes a minute to build the muscle memory for the claw. Naturally, we just want to grab things with straight fingers.
We do. But once you trust the flat of the blade against your knuckles, you can slice with incredible speed without even looking down.
So the grip is solid, the shield is up. Now we translate the static posture into dynamic movement, the mechanics of the slice.
The fun part.
And the golden rule here is that we are utilizing a circular rocking motion. We are slicing, never slamming the blade straight down.
This is where we introduce the rolling slice.
Yeah.
It often gets compared to the wheel of a locomotive.
The choo-choo technique.
Exactly. It is a continuous fluid cycle. You push the knife forward and down, then lift it back and up, then push forward and down again. The blade glides.
Now, let me play devil's advocate here for a second, because if you watch certain aggressive cooking shows, you often see chefs doing a rapid-fire up-and-down guillotine chop.
Rapid hacking.
Yeah, whack, 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 straight down into the board. If I'm trying to power through a mountain of celery, why not just chop straight down like that? It genuinely feels faster.
I mean, it might look flashy on television, but it fundamentally misunderstands what a knife edge actually is at a microscopic level.
What do you mean?
Well, even the finest, smoothest-looking chef's knife is not perfectly smooth. Under a microscope, that edge is made of tiny, jagged serrations.
Microscopic teeth, like a microscopic saw.
Exactly. And to utilize a saw, you have to push it forward and drag it back. Pushing the knife forward as you press down utilizes those tiny teeth to cleanly sever the cellular structure of the food.
Oh, so if you just chop straight down like a
They're
guillotine.
not slicing. You are applying blunt force trauma.
Yeah.
You're crushing the food, smashing the cell walls, and just blowing out all the internal moisture.
Wait, and this brings us right back to our opening point about onions.
Yes.
This is the exact food science behind why people cry when dicing onions. When you use a dull knife, or when you chop straight down, you physically crush the onion cells.
Exactly.
That crushing ruptures the vacuoles inside the cells, which mix enzymes together and create that volatile sulfur gas that hits your eyes and makes you tear up.
Precisely. A surgically cleaned slice from a sharp blade gliding forward severs the cells cleanly. It leaves the majority of those volatile compounds trapped safely inside the onion where they belong.
That is wild.
Yeah, clean slices mean superior texture, better moisture retention, and purer flavors. You aren't leaving your ingredients' essential oils smeared across your cutting board.
You see this instantly with herbs, too.
Oh, absolutely.
If you watch someone violently chop fresh basil with a dull knife using a downward hacking motion, the edges of the basil turn black almost immediately.
It bruised the leaves.
Yeah, causing rapid enzymatic browning, and all the aromatic oils just evaporate into the air.
Which is why we use a pivot technique for delicate, tightly bunched herbs.
How does that work?
Well, you gather your parsley or cilantro into a tight mound. And instead of lifting the whole knife, you keep the precise tip of the blade planted firmly onto the cutting board. It acts as an anchor point.
So the tip never leaves the board at all.
Right. You rest your guiding hand lightly on the front of the spine, and the heel of the knife does a rapid, controlled up and down arc.
Ah, so the blade rocks over the herbs cleanly.
Exactly. Utilizing those microscopic teeth, delivering an incredibly fine mince without bruising the leaves or scattering green confetti all over your kitchen.
The mechanics of the slice really dictate the quality of the ingredient. So, with our grips locked and our locomotive motion fluid, we can start applying this physics to actual geometric shapes.
The fundamental cuts.
Yes, let's start with the base layer, the rough chop.
A rough chop is your rustic workhorse. Think about garlic. You peel the cloves, apply a firm but controlled smash with the flat of the blade to crack the structure.
Which actually helps release the allicin, right? The
Yeah.
compound responsible for garlic's pungent flavor.
Exactly. And then you utilize that rocking pivot motion. You sweep the knife through the pile until the pieces are thoroughly broken down. The geometry doesn't have to be perfect. The goal is just rapid, efficient breakdown.
But the rough chop is just the warm-up. It's when we move into the realm of precision cuts that the true architecture of professional cooking emerges.
Definitely.
If you want a dish to cook evenly and present beautifully, you must master the rigid progression of geometric cuts. And the absolute first step in precision geometry is squaring off your vegetables.
Because nature does not grow in right angles.
Right.
Carrots, potatoes, beets, they are entirely irregular. We have to manufacture our own baseline. You slice off the rounded sides to create a perfect flat-sided rectangular block.
I always think of this like milling timber at a lumber yard. You cannot build a structurally sound, uniform piece of furniture using raw, round logs.
No, you can't.
You have to run the log through the sawmill to create a rectangular beam before you can start cutting your planks. We are essentially making culinary lumber.
I like that. Culinary lumber.
I know what a lot of people are thinking here. In an era where we are hyper-aware of food waste, slicing the four rounded sides off a potato just to get a perfect rectangle feels incredibly wasteful. I mean, you are discarding 20% of the vegetable.
It's a great point, but it highlights the hidden economy of a professional kitchen. A good kitchen operates on a strict zero-waste philosophy.
So what happens to the scraps?
Those irregular scraps from squaring off never go in the trash. They go into a dedicated bin to become the backbone of your secondary preparations.
Like stocks.
Yes, you use them for your mirepoix, the aromatic base for your stocks and sauces, or you roast them down for purees, or they just go into the staff meal.
That makes a lot of sense.
You extract absolutely every drop of flavor from those scraps while still achieving the pristine geometry required for your final plate presentation.
You separate the function from the presentation. I love that. Okay, so We've milled our vegetable into a clean, flat-sided rectangular block. From here, the progression is pure, scalable math.
It really is.
You take that block and you slice it lengthwise into even, flat slabs of the exact same thickness. Then you stack those flat slabs back on top of each other and you slice straight down through the stack to create uniform sticks.
And this is where the terminology of the classic matchsticks comes in. If you slice your slabs a quarter-inch thick and then slice your stacked sticks a quarter-inch wide, you have built the bâtonnet.
The bâtonnet, it sounds very hot cuisine, but in practical terms, it is a sturdy, quarter-inch thick stick, usually a couple of inches long.
Yeah, if you picture a really high-end, thick-cut French fry, you're picturing a perfect bâtonnet.
And the beauty of this system is that it scales perfectly, right?
Exactly. If you apply that exact same progression, but you tighten your measurements drastically, slicing your slabs a microscopic 1/16 of an inch thick, and then cutting your sticks a 1/16 of an inch wide, you have achieved the fine julienne.
A delicate, incredibly precise little matchstick.
Yes.
So we have our structural sticks, the sturdy bâtonnet or the delicate fine julienne. This brings us to the final transformation. We gather those sticks tightly together, line up the ends perfectly with our guiding claw hand, and we cross-cut across the sticks.
Cross-cutting the sticks is what yields the cube, or the dice.
And the final size of your dice is entirely dictated by the size of the sticks you just manufactured.
Exactly. If you cross-cut that quarter-inch bâtonnet at quarter-inch intervals, you yield a perfect small dice, a geometric cube exactly a quarter of an inch on all sides.
And obviously, if you started with a massive half-inch thick stick, cross-cutting that yields a medium dice.
Right. But the true test of knife control is at the other end of the spectrum.
Just tiny ones.
Yes. If you take those delicate 1/16 of an inch fine julienne matchsticks and you cut them, you produce the brunoise.
The fine brunoise.
These are minuscule 1/16 of an inch cubes. Executing a perfect brunoise requires immense discipline.
I can imagine.
Your blade must be lethally sharp, your pinch grip must be completely rigid to prevent lateral wobble, and your rolling motion must be flawlessly smooth.
Yeah.
If you try to chop straight down on a julienne stack, you will simply crush the delicate vegetable into a wet paste.
A perfectly executed brunoise is incredible to look at. It's like culinary confetti.
It really is.
But let's elevate this beyond just aesthetics. Let's talk about why we go through all this trouble.
Go ahead.
If I am making a rustic beef stew, a rough chop is totally fine. But if I am making a highly refined sauce, why do I specifically need a fine brunoise of carrot or shallot?
It comes entirely down to thermodynamics and the mathematics of surface
So
area.
it's surface area, okay.
When you cut a vegetable into a brunoise, you are exponentially multiplying the exposed surface area of that ingredient relative to its volume.
Right, because instead of one big chunk hitting the hot pan, you have hundreds of tiny cubes, all with 6 distinct sides exposed to the heat.
Exactly. And that massive increase in surface area means heat penetrates instantly. If you toss a brunoise of carrots into hot butter, the Maillard reaction...
The chemical process of browning and caramelization.
Yes, that happens incredibly fast. The natural sugars release almost immediately. The flavor extraction is rapid and thoroughly homogeneous.
Wow.
In a refined sauce, a brunoise acts almost like a dissolving flavor crystal. It integrates completely without leaving large, disruptive textures for the diner to chew on.
So the geometry fundamentally alters the chemical reaction in the pan. The cut dictates the flavor extraction. It's fascinating.
It changes everything.
Let's look at the sheer scope of what we've covered in this session.
Oh, you've covered a lot.
We really have. We analyzed the physics of shear force to understand why a simple damp towel secures our environment. We abandoned the baseball bat grip to pinch the actual steel, fusing the center of gravity of the French knife to our arm.
We built a sheer wall of bone with the claw hand.
Yes. We bypassed the bruising guillotine chop to utilize the microscopic tip of the blade in a continuous rolling slice. And finally, we manufactured culinary lumber, moving methodically from the quarter-inch bâtonnet down to the thermodynamic perfection of the fine brunoise.
It is a totally systematic approach to the craft. When your prep work becomes methodical, the chaos of cooking disappears.
It just vanishes.
Yeah, you aren't muscling the knife. You are simply guiding the geometry. You have established a biomechanical foundation that will literally dictate the quality of every single meal you prepare from this day forward.
And I want to leave you with a final thought to mull over the next time you step up to your cutting board. We just established that massive surface area changes how fast an ingredient cooks and caramelizes.
Right.
But does the precise geometric shape actually change how the food tastes on your palate if it's served raw?
Oh, that is an incredible question. Does a perfectly uniform fine brunoise of raw apple actually taste sweeter than a rough, jagged chunk simply because the microscopic cubes blanket your taste buds more efficiently?
Delivering a faster, more concentrated release of fructose?
Yes.
I highly encourage you to run that experiment in your own kitchen. Take an apple or a carrot, cut half of it into a lazy, uneven rough chop, and then take your time to cut the other half into a flawless 1/16 of an inch fine brunoise.
Eat them side by side.
Exactly. Taste the profound difference that pure geometry makes to your palate. Trust the steel, lock in your grip, and respect the blade.